Every crane that built the Brooklyn Bridge was anchored to the Brooklyn Bridge. Every derrick that erected the George Washington Bridge towers climbed up those towers using the steel it had just set in place. And the 600-ton creeper cranes on the Sydney Harbour Bridge spent 4 years crawling up both sides of the arch until they met at the crown, and then had to be taken apart by progressively smaller cranes. A 25-ton derrick dismantled the 600-ton creeper. Then a 7-ton crane dismantled the 25-ton derrick. Then a hand winch removed the 7-ton crane. Before hydraulics, every bridge crane in the world was built from the bridge it was building. When the bridge was finished, the crane had to erase itself. But this story does not start with a crane. It starts with a rope. In 1841, on a farm in Saxonburg, Pennsylvania, a German immigrant named John Augustus Roebling strung wire on a hand-cranked rope walk and twisted it into the first successful American wire rope. The idea was simple. Take individual wires, braid them together under tension, and the resulting cable outlasts Kentucky hemp by 4 to 1. Roebling had come to America from Mühlhausen, Prussia in 1831, trained at the Royal Polytechnic Institute in Berlin, where he studied under the philosopher Hegel, and spent a decade farming and canal building before the rope idea took hold. The problem he was trying to solve was practical. The Allegheny Portage Railroad used inclined planes to haul canal boats over the Appalachian Mountains, and the hemp ropes that pulled the boats up the slopes kept snapping. Roebling's wire rope solved it on the first attempt. He filed U.S. Patent 2720 for his manufacturing method, and that single patent changed 2 industries at once. It made suspension bridges possible, because now you could spin cables strong enough to hold a roadway across a river. And it made bridge cranes possible, because every hoist line, every boom pendant, every cableway that would lift steel across America's rivers for the next century would run on Roebling wire. The rope and the crane were born together. Roebling understood something that none of his competitors grasped. He did not just sell rope. He built a factory in Trenton, New Jersey that produced the wire. He designed the machines that spun that wire into cables, and then he designed the bridges those cables would hold. One family controlled every step, from the raw iron ore to the finished span. That vertical integration, where the rope maker was also the bridge builder and the crane operator, set the template for American bridge work for the next 100 years. We should talk about the machines themselves, because bridge cranes were not one thing. They were 4 distinct machines, and each one solved a different problem that you encounter when you try to lift thousands of tons of steel across open water. The first was the guy derrick. Picture a single wooden or steel mast held upright by radiating guy wires, with a boom hinged at its base that could swing in a full circle. The beauty of the guy derrick was its ability to jump itself upward. The boom would hoist the mast to the next level, the guys would be re-anchored to the new steel, and the whole machine climbed another story. This is how every major suspension bridge tower in America went up between the 1880s and the 1960s. The same guy derricks that erected the Empire State Building in 410 days worked the same way on bridge towers, climbing with the structure as it rose. The second machine was the stiff-leg derrick. Instead of flexible guy wires, it used 2 rigid back legs bolted to a platform at fixed angles, usually around 60 degrees from the mast. Stiff legs lived on barges and on fixed foundations along riverbanks, and they became the workhorses of waterside construction because their rigid geometry made them stable in current and wind. The third was the gantry traveler, a crane that rode on rails along the completed section of a bridge deck, reaching forward to pick up the next truss panel or girder section ahead of itself and setting it in place. This is how long truss bridges and railway bridges went together across the entire continent, panel by panel, the traveler feeding on the structure it was extending. And the fourth was the creeper derrick. a specialized self-climbing machine designed specifically for arch bridges. It hauled itself up the inclined top chord of an arch using its own winches, acting against tieback cables anchored to the completed portion of the span below. Like and subscribe if you want to see more construction history like this. What made all four machines fundamentally different from a modern hydraulic crane was that they had no independence. They could not drive to the job site on rubber tires. They could not park in a staging area and reach over a fence. Every one of them was built from the structure it was building. The counterweight came from the bridge steel. The rails came from the bridge deck. The anchorage came from the bridge foundations. Erection sequence and bridge design were a single engineering problem, and the construction superintendents who planned bridge erection spent as much time designing the temporary crane installations as the chief engineers spent designing the permanent spans. That problem first came together in full scale on the Brooklyn Bridge. John Roebling designed the bridge, but he never saw it built. In the summer of 1869, while surveying the Brooklyn Tower site, his foot was crushed between a ferry piling and the dock. He refused amputation, insisting on water therapy instead. Tetanus set in within days, and he died on July 22, 1869, 24 days after the accident. His son, Washington Roebling, took over as chief engineer at the age of 32. Washington supervised the sinking of the massive pneumatic caissons, wooden boxes the size of city blocks that were sunk to the riverbed and pressurized with compressed air so workers could dig the foundations in dry conditions. The work was brutal. Men descended into the caissons through airlocks and dug mud and rock in candlelit chambers while breathing compressed air at pressures up to 35 pounds per square inch. Many developed caisson disease, what we now call decompression sickness, or the bends. Washington Roebling himself was paralyzed by it in 1872 and spent the remaining 11 years of construction supervising from his apartment in Brooklyn Heights through a telescope, with his wife Emily Warren Roebling carrying his instructions to the site and effectively managing the daily operations. The Brooklyn Bridge towers rose 276 feet above the East River, and they were built by stiff-leg derricks mounted on timber cribs that climbed with the granite masonry, course by course, lifting stone blocks from barges moored below. Each granite block weighed between 3 and 6 tons, and the derricks hoisted them with manila rope running through iron sheaves powered by steam donkey engines on the riverbank. Once the towers were finished, Roebling's cable spinning system took over. Traveling wheels shuttled single wires back and forth across catwalks strung between the towers, laying wire after wire until 4 cables, each 15 3/4 inches in diameter, held 14,060 miles of galvanized steel wire. Every foot of that wire came from the Roebling plant in Trenton. The spinning wheels ran on Roebling rope. The bridge was held by Roebling cable. Between 20 and 30 workers died during the 14 years of construction, many from falls off the towers and catwalks, several from caisson disease, and the chief engineer himself from a dock accident before the first stone was ever set. The Brooklyn Bridge opened on May 24, 1883, and it proved that cable-operated cranes could build structures at a scale that seemed impossible a generation earlier. But it also proved something darker. The men who worked those derricks had no safety equipment, no harnesses, no nets, no hard hats. When a rigger lost his footing on a timber crib 200 feet above the East River, there was nothing between him and the water. The falls were silent. The other men on the tower would hear a splash and keep working, because stopping meant the steam engines below would lose pressure, and the whole lifting sequence would have to restart the next morning. Before Brooklyn, a bridge in St. Louis had already demonstrated the potential and the danger of cable-operated construction over deep water. The Eads Bridge, completed in 1874, was the first major bridge in the world built entirely of steel rather than iron. Captain James Buchanan Eads, a self-taught engineer who had made his fortune salvaging sunken steamboats from the Mississippi River bottom using diving bells, designed a triple arch span with 3 500-foot ribbed arches resting on stone piers sunk to bedrock through pneumatic caissons. The caisson work at St. Louis was even more brutal than Brooklyn's. Workers descended to depths of over 100 feet below the river surface, breathing compressed air at pressures that caused nosebleeds, joint pain, and paralysis. 14 men died from caisson disease during the 3-year foundation campaign. The arch ribs themselves were erected by cantilevering from the piers, using temporary cable stays anchored to the finished masonry, the same principle Lindenthal would later refine at Hell Gate. Eads Bridge proved that cables and derricks could build arches over a navigable river without blocking traffic below. It also proved that the men doing the work would pay for every engineering advance with their bodies. But the real engineering breakthrough in crane technology came 40 years later, when a bridge builder named Gustav Lindenthal attempted something that forced the industry to invent entirely new lifting techniques. Lindenthal's Hell Gate Bridge across the East River was a 977-foot steel arch, and it crossed a navigable shipping channel at a point where the tidal currents ran at dangerous speeds. False work was not an option. You simply could not build temporary supports in the river because ocean-going vessels had to pass underneath throughout construction. Therefore, the American Bridge Company cantilevered the 2 arch halves out from the abutments on each shore, holding them in place with massive temporary backstays rated to resist hundreds of thousands of pounds of overturning force. And here is where the engineering becomes genuinely brilliant. The counterweights for those backstays were not dead weight shipped to the site. They were made from the very plate girders that would later become the approach viaducts. The temporary structure that kept the arch from collapsing during construction became the permanent structure that carried trains after the arch was closed. Lindenthal was also the first American engineer to instrument a bridge during construction. He attached Howard extensometers to the eye-bars of the arch to measure live stress in the steel as the cranes added weight to the cantilever arms. His measurements revealed that the eye-bar loads were uneven, a condition that could have caused a catastrophic failure if left uncorrected. But because he was monitoring in real time, his crews equalized the loads with hydraulic jack adjustments before closing the arch in September 1915. On the approach viaducts, McClintock Marshall used 50-ton steel derrick cars and locomotive cranes running on temporary track laid along the deck. Gantry travelers erected 11,250 tons of truss steel, picking members from a material track at top chord level. The division of machines became the model for every long-span bridge built over the next 50 years. Floating derricks in the river delivered steel to the base. Gantry travelers on the deck set pieces into final position. Locomotive cranes on temporary rails moved material along the approaches. Each machine fed the next in a choreography that required the same steel to serve as both cargo and crane platform simultaneously. We spent weeks researching what came next. 1931 turns out to be the single most important year in the history of bridge cranes. We have covered the rope, the 4 machines, and the bridges that proved the system worked. Now comes the year when everything peaked. This is part 4 of 6, and here the entire toolkit comes together on 3 bridges at once. One engineer designed 3 bridges that opened within weeks of each other, and each one used a different crane system. Othmar Ammann had worked for Lindenthal on Hell Gate, and he had absorbed everything the older man knew about cantilevering steel over open water. His George Washington Bridge across the Hudson River was a 3,500-foot suspension span, nearly double the previous world record held by the Ambassador Bridge in Detroit. The 604-foot steel towers were erected by guy derricks that climbed with the lattice steelwork, jumping themselves upward story by story in the same technique used on every suspension tower since the 1880s. Ammann ultimately left the towers unclad, abandoning the planned granite facing designed by architect Cass Gilbert, because the open steelwork was both lighter and cheaper. John A. Roebling's Sons Company then spun the 4 main cables of 26,474 wires each, over 10 months from July 1929 through August 1930, using dozens of spinning reels at the New York Anchorage dock. Each reel held 30 miles of wire. A self-propelled gantry traveler, photographed repeatedly by Port Authority engineer Frank Trani, then picked floor beam sections hoisted from barges below and set them onto the suspender cables to form the roadway deck. An estimated 12 or 13 workers died during the 4-year construction, mostly from falls, and one from an explosion at the New Jersey Palisades anchorage. The bridge opened on October 25, 1931, 6 months ahead of schedule and under its $60 million budget. 3 weeks later, Ammann's Bayonne Bridge across the Kilvan opened on November 15th as the world's longest steel arch at 1,675 feet, 25 feet longer than the Sydney Harbour Bridge, then under construction in Australia. The erection method was the opposite of Lindenthal's Hellgate approach. American Bridge chose falsework over cantilevering because the river bottom was solid rock, and the falsework itself was made of steel members that were later incorporated into the permanent bridge. Floating derricks in the Kilvan Coal Channel lifted prefabricated truss segments of high-alloy steel into position, while travelers on the partially completed arch guided them into final alignment. The entire bridge used only 16,000 tons of steel. For comparison, the Sydney Harbour Bridge needed 37,000 tons for a span of roughly similar length. The American Institute of Steel Construction named the Bayonne the most beautiful steel bridge of 1931, ranking it ahead of the George Washington. And in Australia that same year, the most spectacular cable crane operation in bridge construction history was reaching its climax. 2 600-ton creeper cranes had been crawling up the arch of the Sydney Harbour Bridge for 4 years, one advancing from each shore, each machine combining a main jib with a lifting capacity measured in hundreds of tons, a 5-ton wall crane for lighter work, 2 2.5-ton stage derricks for positioning, and a built-up link frame climbing mechanism that hauled the entire assembly up the sloping top chord, using its own winches pulling against tie-back cables anchored to the completed arch below. The engineering firm Dorman Long of Middlesbrough, England, designed these cranes specifically for the Harbour Bridge, and they cost £50,000 to fabricate and erect. Like and subscribe to follow this channel. When the 2 halves of the arch finally met at the crown, the cranes had to come down. But you cannot simply lower a 600-ton machine from the apex of an arch bridge. Therefore, a 25-ton derrick dismantled each 600-ton creeper piece by piece. Then a 7-ton crane dismantled the 25-ton derrick. Then a hand winch removed the 7-ton crane. The whole operation ran in reverse, like a set of nesting dolls being put back inside each other, high above Sydney Harbour, with nothing beneath but water. Now we come to part 5, and this is the part of the story that almost never gets told. Because one of the most overlooked chapters of bridge crane history is not about the machines at all. It is about who was actually on them, who rode the booms and caught the loads and worked the hoisting cables hundreds of feet above the water with nothing between them and the river below. Many of them were Mohawk. The tradition began in 1886 at Kahnawake, a Mohawk community on the south shore of the St. Lawrence River near Montreal, when Dominion Bridge Company hired Mohawk men as laborers on a Canadian Pacific Railway bridge. The work was supposed to be menial, hauling rivets, carrying tools, fetching water. But foremen noticed something they had never seen before. The Mohawk workers climbed the partially completed girders with absolute ease, walking along narrow steel flanges at heights that made other workers freeze. Dominion began training them as riveters and structural connectors, and within a single generation, Mohawk Ironworkers were building steel structures across the northeastern United States and Canada. Then came the disaster that reshaped the entire community. On August 29, 1907, at approximately 5:30 in the afternoon, the south anchor arm of the Quebec Bridge collapsed without warning during construction. The partially completed cantilever span dropped into the St. Lawrence River in 15 seconds, carrying 75 men with it. 33 of the dead were Mohawks from Kahnawake. The losses were concentrated because the community had sent its best men to a single project. 5 family names disappeared from Kahnawake entirely that afternoon. 24 women became widows. 56 children lost their fathers. The scale of grief in a community of fewer than 2,000 people was almost incomprehensible. But instead of ending Mohawk ironworking, the Quebec Bridge disaster transformed it forever. The women of Kahnawake made a collective decision that would shape American construction for the next 60 years. They insisted that their men never again concentrate on a single project. The ironworkers had to spread out across many jobs in small crews, so that no one collapse could ever devastate the community again. That decision created the practice known as booming out. Mohawk ironworkers traveled in crews of 3 or 4 from job to job, following the steel wherever it went. They worked on the Hellgate Bridge in 1916, the George Washington Bridge Towers, the Empire State Building, the Waldorf Astoria Hotel, the Triborough Bridge, the Golden Gate Bridge, and the Chrysler Building, where Mohawk Skywalkers from the Kahnawake Reservation riveted Krupp Nirosta stainless steel 1,000 feet above Lexington Avenue, while speaking their own language, Kahnawake. By the 1950s, a neighborhood in Brooklyn's North Gowanus known as Little Kahnawake housed over 700 Mohawk ironworkers and their families. A 1925 court ruling in the case of Paul K. Diabo guaranteed their free passage across the United States and Canada border under the Jay Treaty. The rhythm of their work followed the cranes. On a typical bridge tower job, a crew of 4 connectors would ride the guy Derrick's load hook up to the working level at dawn. The crane operator, seated in an open cab, bolted to the mast with no enclosure and no heat, took signals from a pusher on the steel using hand signs and bell codes. 1 bell meant hoist, 2 bells meant lower, 3 bells meant swing. There was no radio communication. The operator had to read the pusher's hands across a gap of 50 or 100 feet while managing friction brakes that controlled thousands of pounds of swinging steel. If the wind picked up or a cable stretched, the load would start to pendulum, and the connectors standing on a 12-inch flange with no tie-off had to catch it with their hands and bolt it before it swung back. The Mohawk connectors were famous for their ability to ride the steel, shifting their weight instinctively as a beam swayed under them, in a way that other workers could not learn no matter how long they tried. The last great project of the cable crane era brought the human cost of this work into its sharpest focus. But before the Verrazzano, one more bridge demonstrated the full scale of what floating crane fleets could accomplish. The Mackinac Bridge across the Straits of Mackinac in Michigan, built between 1954 and 1957, required the largest bridge construction fleet ever assembled. The contractor Merritt Chapman and Scott Corporation, traceable to Captain Israel J. Merritt's 1860 Coast Wrecking Company, and known across the maritime industry by its Black Horse House flag, won a $25.7 million foundation contract that required sinking 34 piers in up to 300 feet of water through pneumatic caissons. The fleet included derrick barges, material barges, tugboats, crew boats, and floating concrete plants that had to operate in straits where winds reached 60 miles per hour, and winter ice closed the site for 5 months each year. Chief Engineer David Steinman designed the bridge to flex 20 feet laterally in a 70-mile-per-hour wind. and the suspension cable spinning required traveling wheels to make continuous passes across catwalks 400 feet above open water in conditions that frequently grounded the crew boats below. 5 men died during construction. Merritt Chapman's decline in the late 1960s, brought on by financier Lewis Wolfson's overexpansion, stock manipulation, and eventual criminal fraud conviction, effectively ended the era of single-firm dominance in American marine heavy construction. The cranes on Merritt Chapman's barges and on bridge projects across the country overwhelmingly came from one factory. Clyde Iron Works of Duluth, Minnesota, founded in 1889, built the Whirly crane, a 360-degree revolving machine that became the standard heavy-lift crane for water construction. Clyde Whirlies went into the Panama Canal locks, Grand Coulee Dam, the Empire State Building, and the Golden Gate Bridge. The same Clyde Iron technology that swung 20-ton concrete buckets across Black Canyon every 78 seconds at Hoover Dam also lifted bridge deck sections across New York Harbor. The Verrazzano-Narrows Bridge, designed by the 80-year-old Othmar Ammann, compressed the entire cable crane toolkit into a single 5-year project. Bethlehem Steel built the 693-foot Staten Island Tower using derricks. Harris Structural Steel built the Brooklyn Tower. American Bridge spun the 4 cables over 6 months in 1963, making 104,432 passes of the spinning wheels. The 60 deck sections, each weighing 40 tons, were fabricated at a Jersey City assembly line, combined at a Bayonne steelworks, floated to the site by barge, and lifted into position by the Clyde Iron Works hoist that the manufacturer called the world's largest portable crane. 3 workers died on the Verrazzano. The first was 58-year-old Paul Bassett, who fell inside the Brooklyn Tower in August 1962. The third was Gerard McKee, a 19-year-old member of Ironworkers Local 40, who on October 9, 1963, slipped through a gap in a catwalk plank 400 feet above the Narrows. The men on the cables watched his shirt blow off his back as he fell. His body was never recovered from the water below. McKee's death triggered a 5-day strike in December 1963 that won something no American bridge project had ever had: safety nets under the deck. An ironworker named Bob Walsh later said those nets saved his own life on 3 separate occasions and caught other men who fell after him. Every cable crane operator, every rigger, every connector who built the bridges we drive across today did it without a net underneath them, until a 19-year-old kid fell through a hole in the planking, and the men who worked beside him refused to go back up without one. Like and subscribe for more stories about the workers who built America's infrastructure. We are now at the final part of this story, and it begins in a 2-car garage in rural Pennsylvania. In 1947, in Shady Grove, Pennsylvania, a man named John L. Grove, his brother Dwight, and their partner Wayne Nicary built a rubber-tired crane in a rented garage to move steel for their farm wagon business. The machine was crude. It used a surplus military hydraulic cylinder to raise and lower its boom, but it could drive itself to the job site, set up without bolts or guy wires, lift a load, and drive away. No foundations, no anchoring to the structure, no team of riggers to assemble and disassemble it. By 1952, they had produced the first mobile hydraulic industrial crane suitable for commercial construction. By 1968, they had built the world's first slewing rough terrain crane. By 1974, they had a 100-ton hydraulic truck crane on the market, the Grove TM 1075. By the mid-1970s, roughly 140 hydraulic crane manufacturers were competing across 25 countries. The crane had finally been separated from the structure it was building. For the first time in 130 years, a lifting machine did not need the bridge, the dam, or the building in order to function. The speed of the transition caught the entire derrick industry off guard. In 1975, an American bridge contractor would typically spend 6 to 8 weeks assembling a guy derrick system on a tower site, bolting together the mast sections, rigging the guys, testing the hoist drums, and anchoring the whole assembly to the foundation steel. A hydraulic truck crane could drive to the same site, set up its outriggers, and start lifting within 2 hours. The cost difference was devastating. A guy derrick required a crew of 8 to 12 riggers working for weeks. A hydraulic crane required 1 operator and 1 oiler. Bridge contractors who had relied on Clyde Iron whirlies and American hoist stiff-leg derricks for decades began renting Grove and Liebherr hydraulic cranes instead. And once the rental model took hold, the economics of manufacturing purpose-built derricks collapsed almost overnight. The consequences for the cable crane industry were total. 17 of 22 American lattice boom crane plants closed between 1981 and 1985. 10 telescopic crane manufacturers went out of business in the same 4 years. Clyde Iron's Duluth Works, the factory that had built the whirly cranes for Hoover Dam, Grand Coulee, and the Verrazzano, shut down in 1986 after nearly a century of production. The company moved to St. Paul and merged with American Hoist and Derrick's Marine Division to form Clyde. Grove itself was eventually acquired by Manitowoc in 2002 for $271 million. The entire industry that had built every major bridge, dam, and skyscraper in America for over 100 years was gone within a single decade. But the machines themselves refused to die. That Clyde Iron hoist from the Verrazzano job, the one they called the world's largest portable crane in 1961, was sold to J. Ray McDermott, then to Weeks Marine, and renamed the Weeks 533. It became the largest revolving floating crane on the United States East Coast, a machine that has outlived every company that ever owned it. In January 2009, the Weeks 533 lifted the fuselage of U.S. Airways Flight 1549 out of the Hudson River after Captain Sully Sullenberger's emergency water landing. And in March 2024, the Weeks 533 was floating in the Patapisco River in Baltimore, pulling twisted steel wreckage of the Francis Scott Key Bridge out of the water after a container ship struck the bridge's support column and brought the entire span down in seconds. The Weeks 533 worked around the clock on that salvage operation, its 63-year-old revolving mechanism swinging loads that its Clyde Iron designers in Duluth could never have imagined it would still be handling. The crane barge working right next to it in Baltimore was the Chesapeake 1000. That vessel was built in 1972 by Sun Shipbuilding with a purpose that had nothing to do with bridges or salvage. It was designed to lift a 630-ton gimbal onto the CIA spy ship Glomar Explorer, the vessel that secretly attempted to raise a sunken Soviet submarine designated K-129 from 3 miles below the surface of the Pacific Ocean during the Cold War. A crane built for espionage and a crane built for the Verrazzano-Narrows Bridge, both over 50 years old, side by side in Baltimore Harbor, doing the same work that Captain Israel Merritt's salvage tugs did in 1860, lifting fallen iron out of American waterways. The cable crane did not completely vanish. Derricks retreated to 2 niches where they still outperform anything hydraulic. One is skyscraper dismantling, where companies like Timberland Equipment in Ontario and F&M Mafco manufacture derricks that break down into 350-pound sections, small enough to fit in a freight elevator. The other is bridge construction, where the derrick's ability to anchor directly into the structure remains unmatched. As F&M Mafco puts it, by building the bridge from the bridge, you eliminate the instability of barge-mounted cranes fighting wind, current, and the wake from passing boats. The American Bridge Company used a purpose-designed 100-ton cableway to build the New River Gorge Bridge in West Virginia in 1977, the longest steel arch in the world, at 1,700 feet, and a 1,750 metric ton shear leg crane, a direct descendant of the old Merritt-Chapman barge derricks, assembled the new Bay Bridge self-anchored suspension span in California in 2014. That same shear leg crane is now erecting the Gordie Howe International Bridge approaches over the Detroit River. The technology did not die. It just got quieter. John Roebling twisted wire on a farm in Pennsylvania in 1841. His rope held the Brooklyn Bridge. His rope ran the cranes that built it. 183 years later, a Clyde Iron crane built with Roebling-grade wire rope is still lifting steel out of American harbors. The manufacturers are gone. The plants are closed. The Mohawk Ironworkers of Little Kahnawake scattered from North Gowanus decades ago. But the machines are still out there, on barges in Baltimore, doing exactly what they were built to do. Like and subscribe to follow Construction Legends for more stories like this one.